All right, everybody, thank you for coming back for round two. We're going to go into our lecture from Hammam on rendering and lighting optimization and techniques and tools. So we're going to step it up a notch, and I'm going to turn it over to Hammam.
Thank you, Brian. So, hello and welcome everyone to real-time rendering in Unreal Engine 4. I am Hammam Bahnasi. I'm a technical artist at Epic Games. I have a relatively long background in game development, where my main interest is graphic techniques and procedural content generation. So, the main goal for today's masterclass is to explain and visualize the entire rendering process that happens in real-time engine like Unreal 4. So the goal of this is to develop an overview of all the features that are available in Unreal Engine and understand some of the challenges and restrictions we already saw that are in the pipeline and what are the available solutions for us. So as a result, we will be able to understand the big picture of performance and workflow implications. So this is our agenda for today. We will start with a friendly intro about some real-time rendering concepts. Then we will move on to the rendering steps that a real-time engine has to do in order to generate our final image on the screen. So there's a few things that need to be done before rendering. Then we move on to geometry rendering and then rasterizing the results on G-buffers and so on and so forth. So let's start first with the intro. So important thing when we are talking about real-time rendering as opposed to offline renders that we are used to do with Maya renders like V-Ray or Arnold, is here the priority is not only to generate beautiful images, but also to have some interactive frame rate. Just to have a sense of how long a frame takes to render in Unreal, let me show you this scene here. So relatively, it's, at least for me, I find it's an interesting scene. So if we look at stat FPS and see here in the top right corner, we see this number, which tells us how much each frame is taking Unreal to render it. So in this case, for that scene, it's taking 8 milliseconds. And we're not talking about minutes or hours like with offline renderers. We're talking not even 1 second. This is millisecond, which is 1/1000 of a second. So imagine how much fast real-time engine had to generate our frames in order to have this interactivity. Okay. So, however, with this priority in, it's a little bit challenging now to have the perfect or the most high-quality results. So we need to always have some balance between three main aspects, which is the quality, of course, the features we use to render our scene, and the performance. With offline renderers like Arnold or V-Ray or other things, we can easily go and maximize the quality and the features. So we can have something like, if we take this triangle here, something on this edge. However, with real-time render engines, this is not the case. We need to have something ideally around the center of this triangle. So in order to do this, the first step we need to do is to identify our frame rate. And of course, this depends heavily on what's our target platform. So if we are targeting something on PCs, we might be aiming for 30 or 60 FPS. If we are targeting VR, we need to be around 90 or even more to have some comfortable experience. Now, with this, of course, we need to have few things. Those are general things or general guidelines. Some of them are very obvious, but still it's important to keep them in mind. The first thing, of course, every content we push to the engine, it needs to be as much efficient as possible. We can't push like any number of triangles or any texture resolution and expect the engine to magically render them at high frame rates. Also, it's important to adjust our pipeline to the engine and hardware restrictions. We already saw in Martin's presentation, like there is some loads we need to take care, like there is MIP maps, there is a few things that we need to adjust in our pipeline. Also, one common technique that we can do is to try to offload some of the expensive parts or calculations that happens usually in runtime and do it in advance and just read the results in runtime. And with engine like Unreal 4, where we have many features or many techniques to achieve a certain result, it's important also to pick the best technique that fits our case to have the maximum quality with the best performance. Okay, so now let's switch to something different a little bit and see what are the components in our PC that usually are involved in real-time rendering. So here we can see a storage device and then a memory, and we have the CPU and the GPU. So what happens, like most of our content, like meshes, textures, materials, everything are stored here on the hard drive or the storage device, and then it's streamed on to the memory. And here, like, there is interesting thing, like the speed of the streaming or of the transfer of the data is different between different components. So we see the speed for transferring data from the hard drive to the memory is, let's say, 1x. It's 10,000 faster when we stream the data from a memory to the CPU and from the memory to the GPU. So that's very interesting. And once we have the data in the memory, the CPU can access this data and start processing it to have the final render. Same thing with the GPU. Now, specifically with the GPU, there is interesting thing about it, which is in one direction, the transfer is super fast. So you can see, like, when we upload the data from the memory to the GPU, we have 10,000 x the speed between the hard drive and the memory. However, when we transfer the data in the other direction, it is much slower. It's almost 100 times slower than the previous direction. So it's important for us, if we are VFX engineers and we want to create some special effect that's run on the GPU, is to make sure we have the data on the GPU, we process everything on the GPU, and publish the results as pixels on the screen. It's not really efficient to do some calculation on the GPU and then bring it back to the memory and then pass it to the CPU, and so, because here we are, like, wasting some performance in the transfer rates. So we saw, like, the CPU and the GPU are the main components that really handle the rendering calculations. One interesting thing about them, they are interdependent. So if we are not careful, they can bottleneck each other, because the flow of the data has to be kind of synchronized. And we need also to make sure we distribute the load in a balanced way between both. Okay, so now let's talk about the shading techniques in real time. Again, in offline rendering, when we want to shade or light a scene using offline renderers like V-Ray or Mentoray, we most of the time use ray tracing techniques because it's accurate, it matches almost how lighting is calculated in the physical world, and it gives us very good results. However, in real-time rendering, at least until now with the current gen hardware, we can't afford doing ray tracing in real time. So we need to find different ways to approximate lighting and shading. And the two common techniques for lighting and shading in real time are deferred shading and forward shading. Unreal 4 supports both, of course. By default, the shading technique in Unreal 4 is deferred shading, but you can, of course, at any time switch to it. So in order to do this, you just need to go to the project settings, and if you search for forward, you will see a checkbox for enabling forward shading. So if you enable this checkbox, basically the editor will ask you to restart the project, and at that time it will be using the forward shading instead of the deferred shading. So what are the differences, or like the high-level features of the deferred shading and forward shading? Deferred shading is a technique that is based on compositing multiple passes and using those passes to calculate the shading. So generally, it is good in rendering or handling dynamic lighting, of course, if we adapt to the guidelines. And also, it's flexible with disabling and enabling features because it's compositing based, so it's really easy to switch features. However, it's a little bit problematic when handling surface attributes like transparency or other things. On the other hand, forward shading, it computes the shading in one pass. There is no multipass, so it renders the geometry, calculate the shading and lighting all in one shot. So because it has all the information, it's good in handling translucent surfaces. And also, it allows us to use hardware anti-aliasing, which is good quality and very fast because it's evaluated on the GPU. However, like the main drawback of forward shading compared to the deferred shading, like when rendering dynamic lights, it has some more performance impacts. So if there's any question at this point, I'll be happy to answer.
Which one renders faster or is more efficient?
Which one is faster? It depends on the scene setup. So like, if you have big resolution, deferred shading probably will be slower and forward shading will be faster. Because, as I mentioned, deferred shading is based on passes, so you need to render multiple passes at very high resolution. That will make the rendering a little bit slower than forward shading, which is render one pass mainly. However, if you have a lot of lights, maybe deferred shading might be better or faster than forward shading, because as I mentioned, forward shading is not really scalable with very high number of lights. And anyways, I'm going to iterate more on the details of those shading techniques later on. Yep.
Hi. Is there a difference in rendering special effects like particles and volumes, that kind of thing?
Yeah, that's a good question. Actually, for particles, because they are heavily translucent rendered, so they are mainly rendered with forward shading. Like if you want to use them with deferred shading, probably you will have to use some opaque particles or something like this. But if you want to render something translucent with a lot of opacity, forward shading is better. Okay. Moving on. So now we can start talking about the actual rendering pipeline. And the first thing we need to cover is some of the calculations that happens before rendering. Now, let's take a look at the main processing unit that are handling the rendering, which is the CPU and the GPU. As I mentioned before, they work together. They are interdependent. So like the rendering process is parallel. And not only this, each one of those branches or spawn multi-threads. So if in Unreal 4, we have three main threads, 2 on the CPU and 1 on the GPU. The first thread on the CPU, we refer to it as the game thread. The second one, we refer to it as the draw thread, and the GPU as an individual thread. As I mentioned, this is like a very simplified representation, and it's very specific to Unreal 4. In reality, what Unreal does is for each one of those threads, it branches also sub-threads, if you want to name them like this, to accelerate the processing. In order to see the time or the calculation time for each one of those threads, we can use also a console command here. So let me first disable the FPS. So there is a console command called stat unit graph. And what that console command will do is will show me the three threads, how much they are taking on my GPU and CPU. So we can see the first thread, which is the game thread on the CPU, is taking around 5 milliseconds. The draw thread is taking this amount, and the GPU is taking that amount. And here also on the bottom, we see some graph, so we can see the timing across also longer range. It's important to understand and monitor those three threads, because it helps us all focus where our optimization need to be done. Is it, are we bottlenecked by the draw or the game or the GPU? We will see this in details later on. I'll disable that and go back. Okay, so we will start with the first thread on the CPU, which is the game thread. And this thread handles a very important thing, which is updating the scene state. So basically, it gives us an answer where each one of our objects will be at a certain frame, the frame we want to render. In order to do this, it has to calculate a lot of systems in order to give us the final transformation of all our objects in the scene. So if there is animation, it has to evaluate the animation at that frame. If we have some physics, it also needs to take the simulation of the physics. If there is AI controlling the movement of the object, also it needs to do this. So it needs to handle everything in order to give us what is the final transform for all our objects in the scene at this current frame. So this is one of the examples where Unreal spawns a lot of threads to handle those in parallel. So it's not going to process animation and then wait until it's done and move on to physics. And no, like it spawns multiple ones, and each one will work in parallel, and then they converge back to the game thread to give us the final result of that transformation. So as I mentioned, the final result is the updated transformation for all our objects. Now we are ready to move on to the next thread. So the next thread mainly it tried to eliminate what needs to be rendered on the scene. So because most of the times when we have big objects, not all those objects are visible for us. Of course, we can ignore this step. However, we will be pushing a lot of objects to be rendered on the GPU, which is not really wise if we are concerned about performance. So this thread is very important, and it does something called occlusion process to build a list of all the visible objects in our scene. Of course, it happens per object. It doesn't happen per triangle because it will be a lot of overhead to process triangle by triangle. So it processes object by object, even if it's less accurate. And there's many, like 4 strategies in Unreal to do this task. Those strategies are different in terms of performance cost. So it starts with the most cheapest one, which is distance culling, and it moves on to the more expensive one, which is frustum culling and occlusion culling. In the next few slides, we will start covering each one of those strategies in detail. So for distance culling, basically it's very simple. The concept is if an object is farther than a certain distance, just don't render it or remove it from the rendering list. Now, this is not on by default in Unreal. You need to manually set it up for your objects. So I'll switch to the editor and show you how to do this. So let's take this thing here. If you expand the rendering section here under LODs, we have a parameter for desired max draw distance. By default, it's set to 0. That means this object won't be culled at all. So if I set it to any value, let's say 500 centimeters, you see now it suddenly disappeared because I'm already farther than 500 centimeters from that object. So if I moved closer, you see now it pop on again. So ideally, you need to set these numbers depending on the size of the object and the distance that will be viewed from. However, if we try to imagine we need to do this for all the objects in the scene, I think that will be a little bit overwhelming task because even for a small scene, you will have maybe tens or maybe hundreds of objects. So doing it manually for each object, it will be a really long thing. So in order to save time and make it more automated, you can use something called culling volumes. So it's available here. You drag it into your level, and you scale it to encapsulate all your levels. I think I already have one here, so let me search. Yep, that's it. I'll zoom out to show you the volume. So you see this is the yellow box, which is the volume for setting the culling distances. So the approach or the way we work with this is you specify certain values for the size of the object and the culling distance. So here you can specify, for example, any object that is smaller than 512, it will be culled after 4,000 centimeters. Same thing here. So for example, if we have an object that is smaller than 1,000 centimeters, it will be culled after this distance, and so on and so forth. So you can set up your distances and sizes, and all the objects within that volume will be automatically culled based on those values. You don't need to go and do it object per object. So this is very useful. So the other approach, which is frustum culling, it's also straightforward. Any object within the camera frustum will be rendered because it's obviously visible for the viewer. Anything outside that frustum will be culled out. This mode is automatically enabled by the editor. You can disable it, and you don't need to mess with it, so it's already working for you. However, one interesting fact about it, let me grab a camera. It's in the water, it's fine. Nice, we have reflection. Yeah, so you can visualize the frustum of your camera here. I think camera frustrums, and you see. So one thing that affects the frustum culling actually directly affected is the field of view. So the bigger the field of view is, the more object will be rendered, obviously, and the more performance will be expensive. So sometimes, like, if you don't have to have like the very wide field of view, you can reduce it, and that will save you a lot of rendering, performance on rendering, because you have less object to be rendered within that field of view. Okay, so the third technique, which is pre-computed visibility. Now, this technique is very nice because it can answer more complex questions. For example, if an object is occluded behind another object. And the way it does it, it divides your scene to a grid of cubes, and each one of our cells, on each one of those cells, it calculates the visibility of the object within that cell and store them for the game to use in runtime. So the actual calculation is not happening on runtime. It's pre-calculated to save some time during runtime. And of course, because it's pre-calculated, it only works with static objects. If we have object that is moving, this technique won't be able to consider it. Now, in the editor, to use this, it's again the same thing. It has a specific volume, which is called pre-computed visibility volume. I think I already have one here. Yep, that's it. Again, you add it to your scene. You scale it to encapsulate all your point area of interest, and that's it. That's all what you need to do. Now, to calculate the visibility, you need to go to the build menu here, and there is a command which says pre-compute static visibility. So once you click this, the editor will go and calculate this information, store them into your level, and make them available for the engine to query them in runtime. We can also visualize the cells if we want. I think it's under the advanced menu here. Let's visualize then. Yep, thank you, Martin. Here you go. So yeah, those are the cells. You see now each cell is like they're already within the volume, and each cell is going to calculate the visibility information for the objects within it. Of course, we can change or control the size of those cells. The smaller the cells, the more accurate the occlusion culling will be. However, the more expensive will be on the memory. Of course, in performance, it won't really make a big difference because they are already pre-calculated. But in memory, it will need more storage. So the final approach, which is similar to the previous one, the main difference is it considers dynamic objects. So if we have an object that are animated or moving within our level, this approach will be able to calculate the visibility for them and include them in the in the rendering list. So there is one interesting console command that we can use it to visualize the occlusion culling. Let me first disable this. Here we go. So if I go inside, so let's say I have a camera that is like this. It's only mainly showing, viewing the wing of the status here. And I want to visualize what's the engine at this point of view is occluded or the object that keeps in for rendering list. So in order to do this, we can use this console command, which is called freeze rendering. And once I execute that command, you see like here on the top of my viewport, it says rendering frozen. Actually, it's not really freezing the rendering because otherwise I won't be able to move anything. What it's doing is actually freezing the occlusion process only. So if I move, it's freezing it at this point. So if I move my camera, I can see like I have a lot of objects are already not rendered because when the camera was at the previous position, those weren't visible for the camera, so it's occluded them. Cool. Yeah, and there is also another console command that allows us to get some stats on the occlusion process, the different process that I explained. So it's init views. Here you can see the different strategy that I explained. It can tell you how many queries it does, like for the frustum culling, how many primitives it takes, like for the static occluding, for the dynamic occlusion. So you get some information on what happens. By the way, if you want to hide anything in terms of stats, you just type stats none, and it will remove all the stats you have shown before. Okay, so a few things to keep in mind regarding the occlusion process. First thing, it's really worth it to manually set up some of the occlusion things like the distance culling using the culling volume or the pre-computed visibility. Because as I mentioned, those are not automatically enabled for you in your level, so you need to go manually and set them up. And the values, as you saw, they are very dependent on your level and your setup. And the cool thing when you did this, it's not going to help for static meshes, but also for other type of actors, like even particles can get occluded. So you save performance on many fronts. Now the question is that if we have many small objects, and those objects are too much, that will be more stress on the CPU because it needs to go and check if they need to be occluded or no. However, at the same time, if we have large but less objects, they will be rarely occluded, and thus it will be more easy for the CPU, but it will increase the stress on the GPU. So at the end, it should be a balance. You need to, based on your world or your level, you need to balance between the object size versus the count of the objects to have a good balance between the CPU and the GPU. Okay, so at the end of this step, the engine has a full list of all the objects that need to be rendered. So, for example, model A will be visible, yes, render it, send it to the GPU. Model C is not visible, ignore it, and so on and so forth. Yeah, any question about the occlusion? Yep.
For dynamic culling,
Mm-hmm.
would it be better to add a scene with a lot of objects that don't have a high poly count, just disable dynamic, and if so, how do you do that?
So if I understand your question, if for dynamic occlusion you prefer to have smaller objects without...
If you had a scene that had a lot of objects,
Yeah.
but not a lot of polygons per object,
Mm-hmm.
maybe you're adding too much to the CPU thread. In that case, would it be better to disable it? And if so, it's there, or would you disable it?
Yeah, like first thing regarding dynamic occlusion, you cannot disable it. What the control you have is only on the distance culling, distance occlusion, and pre-computed visibility. However, what you have control in is the size of the objects and the number of the objects you have in the scene. So in the next few slides, I'll explain a few techniques on how to control this. But anyways, like in terms of strategy, it's always important to have a balance between the object count in your scene. So if you have too many objects, that will be more stressful on the CPU because it needs to check, yeah, this is occluded, not occluded, and whatnot, and so forth. And if you don't, let's say theoretically you are able to disable the occlusion completely, like you're sending tons of objects that might not be visible at the end to the GPU. So we are wasting a lot of performance on the GPU in that case. So again, it's a balance. It depends on your scene, on your level. There is no one strategy that you need to go. You need to analyze your scene and pick the best strategy depending on it. Yep.
Let me bring the mic to you because live stream can't hear you.
Question about the pre-computed culling. I'm a little unclear on what the criteria is for that. So obviously there's distance-based, there's whether it's in the frustum, those are the criteria. But pre-computed, is that one volume looking at another, or how's it deciding what is called and not?
Yeah, it's basically try to calculate if an object is visible from a certain angle. So like if there is an object that is hiding another object, like something behind another object. So yeah, that's some of the criteria that
so
decide.
like one voxel to another? If
Yeah,
you're in
exactly.
One voxel,
Let's say you have a big
position?
wall and you have few objects behind that wall, though those are not going to be visible. So yeah, it knows that information and will store it for the engine.
Thank you.
There's another question right here, Hammam.
Would merging objects take the load off?
Merging objects.
Yeah.
Yeah, of course, if you merge objects, that means you will have less objects to process or for the occlusion, and would be easier for the CPU, so you will save some time on the CPU. However, if when you merge objects, they become very large, so it will be, and you have a camera that is you are only seeing only a fraction of that object. All the object will be rendered. So you might have some inefficiency on the GPU in these cases.
Thank you. Were there any other questions before we carry on? I think
Okay.
you're good.
Cool. Okay, so moving on now to the next step in the rendering pipeline, which is geometry rendering. Now, before going and starting rendering geometry, as we know now, we have all the transformations of the objects. We have what need to be rendered exactly. So the GPU is ready to render it, but in order to be even more efficient, we need also to know which pixel to render. We can render all the objects like without any, but yeah, we might have inefficiency here. So in order to know what pixels from which object to render, we usually generate a depth pass, an early depth pass, and based on the depth of each pixel, we know, okay, the pixel of that object is going to be visible, so let's render it, or it's not going to be visible. To clarify the concept, let me show you this example here. So let's say we have a box that is filling out my screen, and then, like the GPU is going to go for each of those pixels and process them and render the final color of it. Now, let's say we have another teapot or another object, which in this case rendered on top of this. So what happens here is the GPU has processed the pixels twice. Once when it was rendering the orange box, and then next time for rendering the teapot. So this is kind of inefficiency for pixel processing because we touched or processed the pixels twice in this area, and we are only seeing the pixels from the teapot. So one easy solution that we might think of, yeah, why not rendering the teapot first and then render the box? And in that case, we solve the problem. Yeah, for this simple case, it might work. However, if we look at this example, we have the blue object. It's acting as a background and foreground at the same time. So this technique doesn't work. So that's why we need to depend on the depth of those pixels to know if this object or this pixel is behind or in front of another object, and then decide if we need to render it. So ideally, when we do this process, what we end with is something like this. So we render the pixels for all this cube or plane, and then we know in advance, like, we are going to have a teapot in this area, so I'm not going to process its pixels. I'm going to ignore it, and then when rendering the teapot, I'll process its pixels. We can visualize this, but not in the editor. I'm going to show you an external tool, which is super useful. We will be using it all along the presentation. It's called RenderDoc. So what this tool is, basically, it's a GPU profiler that takes a capture of your scene and show you all the GPU activity that happens in order to render the scene from the beginning to the end. So, of course, there is many tools, but this one is open source, and it has a plugin inside Unreal that makes it very easy to capture a frame. So in order to enable this, you need to go to the plugins. And here, if you search for RenderDoc, you will find the plugin for it. You just enable it, restart the editor, and once you've done this, you will have this extra icon here in the viewport. So what we can do is, find the frame that we want to capture, click this icon, and what this icon will basically do is launch the tool and send the frame to it. So now this is the tool, and here we can see the frame that has been captured from the editor. If I double-click on it, it will show me all the steps that the GPU done to render it from the beginning to the end. We're going to cover a few of those steps during this masterclass, but now I just want to show you the prepass or the depth pass that are generated here. So here you see, I'm not sure if it's visible for you, we have something called prepass. If I switch to here and show you the depth and crank this, we can start seeing how the depth pass for the scene is generated at this step. So this is what has been used for knowing in advance what pixels are visible and what not. questions about early ZPass? Yep.
Is it possible to record a sequence?
Is it part to record the
Possible
sequence?
to record a sequence, to have all of those
Multiple,
passes?
you mean multiple frames? Or
Yes, the animation.
no, it only works like one frame. So it captures the current frame that you have specified, and you can see all the steps for the rendering pipeline. So it's basically covering all the things that we are going to explain here.
Okay, thank you.
Yeah.
Other questions? Ah, over here.
Hi, so the question I have is, how does the renderer associate the early Z-pass with an actual object in a scene?
That's a good question. Actually, it doesn't really associate it object per object. What it happens, it's know the position of the pixel on the screen. So what it needs to render an object or a pixel, it knows, okay, at this pixel, I'm going to have this object rendered in this place. And yeah, it's going to be before that. So ignore it or keep it. So it's mainly a spatial relation between, like it's 2D relation between the pixels and the objects.
Other questions?
Hey, you talked about, this was in your previous slideshow, you talked about merging objects might cause long render time. Do you think it's wise to merge objects on your modeling platform before you export to Unreal Engine and then work on it there?
It's up to your workflow. It might be easier to merge them in advance in your DCC and then export them as a merged object to the editor. Or if you find and this is what happens mainly in the gaming world, where we create our scene and then when we profile the performance, we find, okay, we have some issues with the with the certain objects that need to be merged. So we can use the merge tool inside the editor to do this instead of going back to the external DCC, merge the objects and import them back. So you can do both. It's fine.
Any other questions? Okay.
Okay. So we are still talking about this step, which is geometry rendering. Now we are ready to actually rendering some geometry. So in order to be efficient, the GPU render a draw call by draw call, not triangle by triangle. So basically what a draw call is, it's a group of triangles that share the same properties. If we have, let's say, for example, this cylinder here on the far right, it's one object, but it has two separate or two different materials, so that will cause this cylinder to be rendered as two separate draw calls. Draw calls are prepared by the CPU, specifically with the draw threads. And what it happens is basically it needs to distill all the rendering info from the objects and prepare a GPU state that is ready for submission. And again, we can visualize this step here in RenderDoc. So if we go to the base pass, we see here a big list of all the objects or all the draw calls that are generated and submitted to the GPU to render. So if I click on this one, let me highlight the wireframe. So you see there is this small triangle here that's now it's going to be rendered by this draw call. Now this is this column and so on and so forth. So you see it's not rendering triangle by triangle, it's rendering object by object or material by material ID. Depends on how the scene setup is to be more efficient. And the more we move on with the draw call list, we see how the scene is getting rendered gradually. So now we are rendering this thing over there. Yeah. And here we reach the final thing, the final list of the draw calls. This is another slide just to show you the visualization of draw call rendering, but we already saw that in RenderDoc, so we should be fine. Okay, so now a good point we need to understand or to know in advance when we create our scene is what is the reasonable number of draw calls. Of course, this is heavily dependent on the platform you are going to run your application or your experience. But if we are talking about current gen high-end PCs, between 2,000 to 3,000 draw calls, probably this is a reasonable number. If we are getting more than 5,000, that will be a little bit high, and I don't think you will be able to reach something around 30 FPS. You will be dropping probably below that. And the moment you reach something more than 10,000 draw calls, I doubt you will be able to run at interactive frame rate. Most probably the frame rate will be dropping to less than 3 or 4 FPS. Now, of course, on mobile, it's a totally different story. Instead of having few thousand, we are low to few hundreds. So, but the good thing, or the good news, the draw call count is not really dependent on how many objects you have in your scene. Because like someone might say, okay, if like I can't render big open world scenes with this number of draw calls. Yes, you can if you have some good strategy with culling, with occlusion and whatnot, because draw calls is basically going to be counted based on what are the visible objects. So that's why culling is very important. Now, in order to know how many draw calls we have in our scene, there is a console command also for this, which is stat RHI. So here we see, like it shows us the triangle count that's been drawn. In this case, we have around 800,000 triangles. And we have around the draw call primitive calls, which is around 1,100 draw calls, which is very good for, as I mentioned. It's even less than what we mentioned here. So, important thing to keep in mind, draw calls have a huge impact on the CPU draw thread. It has a high overhead because, as I mentioned, it needs to prepare all the rendering information in a GPU state. And most of the times when we have complex scenes, we hit issues with draw calls way before issues with triangle count. So we need always to know where is our bottleneck and focus our optimization in the right direction. If we want to imagine the overhead of a draw call versus the triangles, one good example is in Windows when we copy one single 1 gigabyte file versus copying 1 million 1 kilobyte files. At the end, they both have the same size, but when you copy the first one, it is maybe 100 times faster than copying the second case. So in real time, it's the same thing. Look, if we look at this scene here, we have around 86 million triangles rendered. However, we only have 3,000 draw calls, which is good. And that's why we have a very decent frame rate. It's almost 33 FPS. That's very cool. Now, let's take a look at this case. It's exactly the same setup point of view, except instead of having 3,000 draw calls, now we have 44,000 draw calls. And we have much less triangles. Now, instead of having 86, we have 100,000. And look at how much frame rate we are running now. It's less than 5 milliseconds. That's really big hit, big difference. From 33 FPS, rendering 86 million triangles, to 4 FPS, and here we are rendering only 100,000 triangles. So, big hits. This is another example where I just keep almost the same number of triangles. So now we have 150,000 triangles, but instead of having 44,000 draw calls, it's now around 200 draw calls. And boom, like we have over than 200 FPS. So, to keep in mind that we always need to try to render as many triangles with as few draw calls as possible. And as we saw before in the examples, 50,000 triangles can run much worse than maybe 50 million triangles if we have a not good setup for our scene. So when we optimize, before going directly and start optimizing triangle counts and creating LODs and all those kind of things, try to know what's the bottleneck and focus on that. So now, I'm going to mention here a few strategies for helping optimizing the draw calls. The first one, which is obviously clear for most of you now, is merging objects, because as we mentioned before, draw calls is related directly to how many objects you have and how many unique material IDs we have. So one good strategy is to merge objects, but at the same time, we don't need to go very extreme with this because we might hurt other things negatively. Then the first thing we mentioned before is occlusion. As I mentioned, if we have, instead of having like many objects assembling my scene and I replace it, merge everything into one object, I will never occlude anything in that case. Also, light mapping will be more complex to handle if we have like very huge complex merged objects. Collision calculations might be more expensive because instead of having simple collisions for small individual objects, we will have to be creating more complex collisions to resemble the new merged objects. And last thing, of course, which is important also, it's memory. When we have, especially when we have setups where we have duplicated objects in our level, and we merge all those duplicated objects into one new object, the memory will increase because before it was referencing the same asset. Now it's referencing the fourth asset in one object. So it's always important, like anything with real-time rendering, is to have a good balance between the size and the counts. So some guidelines to pick what objects to merge for optimizing draw calls. It's always a good idea to target low poly objects because those have usually high overhead to render few triangles, which is a waste. So we always try to target those objects. And of course, we need to pick the objects that are within the same area to help occlusion, because if we pick two objects that are very far away, those objects will most of the time won't occlude because they are very the camera will be touching some of them. And of course, we need to make sure when we merge objects, they share the same material, because if we merge objects with different materials, we are not really saving anything on the draw calls. It's not going to do any difference. They are not sharing the same material properties, so there will be still separate draw calls at the end. The fourth point is to try also to find meshes with no collisions or simple collisions, so we can keep the collision calculation relatively low. And one good candidate always is to have to merge the objects that are in distance, like vistas, so they are always fine with culling. So in order to do this in Unreal, we have, as like Martin mentioned before and show us in detail, the merge actor tool. So that's a good saving tool. Like instead of going and doing this process outside Unreal, we can still do it inside Unreal and keep everything available for us. And one cool thing about it, it's also, if you have different materials, it can generate one material to help you reduce the draw call and atlas the material properties into our textures. I'm not going to show this in editor since Martin already covered it, so, but if you have any question you want me to show something specific, I'll be happy to go back to it. The next strategy that's also covered by Martin, it's hierarchical level of details. So we already know that regular loads helps to reducing the triangle counts. But even with regular loads, we can also help draw calls, because what we can do is for the lower loads, we can reduce the number of materials we have. So that will be double win. We are saving some triangles and we are saving draw calls. And of course, we have the hierarchical load, which is a bigger system where we can merge multiple objects and merge their materials and save draw calls and triangles. And again, like I was planning to show this, but I think Martin covered it already. So if we need to go back, I'll be happy to do this. The third approach is instancing. This is very interesting because it's easy to set up and it saves a lot on the draw calls. But of course, in order to make use of it, we need to have copies of objects. Like we can't really have different objects and do instancing with them. So I'll show you in the editor how to do some instancing. First, let me hide. OK, so I'll grab an empty actor. And I'll add a component which is called instance static mesh. So once I add this one, here I can specify what is the source static mesh I want to instance. Let's pick, for example, the cylinder here. And you see now when I set the static mesh, nothing showed here because I didn't specify any instances I want. So in this section, I can start adding instances. So I'll click the plus sign, and you can see now suddenly I have a cylinder. Also, I'm like seeing it from the back. So yeah. So this is the first instance. And for each instance, of course, you can specify the transformation for it, rotation, maybe not this one. Yeah, and so on and so forth. Let's say I want another instance. Here we go. Same thing, I can set the transformation. and so on and so forth. So you see here, like the cool thing about this technique, it doesn't really require any merging or any special preparation, and it's still like all those objects that I instanced here will be rendered as a one draw call. So they are super fast to render. I can spread them as I want in my level, and they will be relatively cheap to render compared to just having multiple actors or multiple cylinders directly instanced here in my level, in my outliner. Okay, so we saw multiple ways to optimize draw calls. Now, what is the best? Again, it's very dependent on your scene setup. I always encourage you to use the best, depending on your case. So you might need to use some merged content with materials. If you have objects that are duplicated, remove them and replace them with instanced objects. If you have some objects that are going to be viewed from far away, from different distances, you might use edgelords, and so on and so forth. So questions about this?
So in another game engine that shall not be mentioned, there's an idea of like when you have material instances like Unreal does, that if the object shares a material instance that is basically based off of a master shader, that it batches all those objects together and makes that into one draw call. Does that happen on the Unreal Engine as well, or does it still consider those instances, even though they're have different textures and attributes, does it then consider those separate draw calls?
In Unreal 4, as long as you are using the static instance mesh that I just showed you, and you set up your instances the way I showed, yeah, it will be considered as instant and will be rendered as in one draw call. However, the engine won't go and automatically figure out, okay, those objects, like, they are the same, they're referencing the same static mesh and they have the same material, and then, okay, I'm going to render them in one draw call. The overhead for doing this in Unreal, unfortunately, is a little bit high, so it's better to do it manually the way I showed you.
Yeah, when you were talking about HLOD, I think you mentioned that you can reduce the amount of material IDs on an object. How do you control that?
Basically, when you generate an edgelords, it will create a new material that is a combination of all the individual materials and atlased into textures that are baked from those different materials. So you end with one material out of maybe many materials, and it will bake the material properties from the individual material into new textures that are used in the new, unique, new one material you have in the edgelord.
I just had a question about the instancing. Someone previously mentioned the situation of having many books coming in from FBX potentially, but then wanting to convert those into instances. I can imagine maybe in the DCC replacing a bunch of books with nulls except for the master and then replacing those. Is there any kind of fast method of doing that? Creating instances out of nulls, for example, based on some master object?
Yeah, I think, again, this a little bit of advertising. The new tool that we are doing with the Montreal team, Datasmith, supposed to do this. So when you export a scene, for example, from Max with multiple instances, it will figure out, okay, those are going to be instances. So it will do the setup for you. So you don't need to go manually and do it the way I did it now. Yeah.
What's that? Sorry.
There's an online question about instancing of particle systems.
Oh, instancing particle system. That's an interesting question. I don't think it's available now, because the static instant mesh editor is only specifically to static meshes. So what happens is for particles, what you can do is create a template and create multiple actors from that template into your scene. But again, it's not going to help the draw calls. It's going to be still separate draw calls and whatnot.
When you instance a mesh, what happens to the light map that's baked into it? Because it might be on the other side of the scene, so maybe the light situation is different.
Yeah, that's very nice question. Actually, light maps are stored into individual texture, so it will still work, but it won't be like as the same. It's not going to be the same workflow with regular static meshes. So what will happen is, yeah, we will have the same static lighting results, but you might notice some differences from when you use regular static meshes, in terms of visual differences, I mean.
Hi, how are particles counted as draw calls or batches? Is it one particle system per draw call, or do you have to break them out, like say 64K or something?
Like, I'm not really sure about the exact numbers with particles, but if you are using GPU particles, I think they are very efficient in terms of batching them into a few draw calls. So you don't end with like one particle per one draw call per particle. Of course, it's going to be now much more efficient, especially if you are using the GPU particles, because you can render hundreds of thousands of particles with very few performance cost. Oh, here we go. It's 1 million even.
Any other questions? Okay, proceed.
Cool. Okay, so we already discussed the draw calls. Now we need to go a little bit deeper and see what happens inside each draw call. So the first thing the GPU process within a draw call is the vertices. And vertex shader usually take care of this process, which is basically a simple program specialized only in vertex processing. So it runs completely in the GPU. It does not do anything except processing vertices. Generally speaking, the input for those vertex shaders are vertex data, like positions or colors and other things. And the output is, again, a vertex data, but in a different space, maybe like word space or screen space. Some of the common tasks for vertex shaders, first is converting the vertex position from local space to word position, or to word space or screen space. Also, it can handle vertex colors or vertex shading. And it handles any additional offset on the vertex position. So let's start with the first one, which is converting the vertex position from the local space to the word space. So we are all familiar with vertices deformation in DCC. Usually, like the vertex position are stored relative to the pivot point of the objects. And we can move then the object and have the transformation of that object and combine, have the final results in the place we want. Now, in order to have that for the GPU, the vertex shader needs to calculate the final vertex position in the word space after considering the pivot transformation and the local vertex positions. We can also look at this in here in RenderDoc. So if I go back to my mesh pipeline, and if I pick, let's say, this object here, so here you see, like, I'm looking at the object. This is the input. This is in the local space. And here we can see all the values that are input to the vertex shader. And on the right here, I have the output of the vertex shader after processing it and converting it to from the 3D space, or from the local space to the screen space. So if I switch here to vertex shader output, you can see now, I'm not sure if it's visible, it's very tiny because that's how it is on my screen. So all the vertices now are converted to the screen space. I think I can tilt it, but you will see like it's squashed, it's like acting weird because now it's all projected on my screen. So this process for converting the transformation from the local space on the left to the screen space on the right is handled completely by the vertex shader. Now, the other task I mentioned also is vertex colors. It's very popular, I think, even in DCC like Maya, where we usually paint weight maps or vertex color to control certain effects like cloth or something like this. It's the same concept in Unreal. So you can use vertex colors to control some shader effects or anything else. And Unreal already have its own tool for painting vertex color. So if you pick any objects, let's try with this guy over here, and you switch to the paint panel, you see like you have an option for painting colors. So let me switch to RGB channel. So I want to paint RGB colors, and you see now I have a brush, and it's showing me all the affected vertices. So what I can do is just pick a color and start painting. And I think you are familiar with like the process. Now the cool thing, this is already painted, so the information, the colors are already stored in that mesh. It's available for me to use it in some certain way. Usually the way we use it is in a material or a shader. So if I created a new material, I'm not going to name it, I can access the vertex color information by creating a node which is called vertex color. So basically this node will allow me to access the vertex color that are painted on that mesh. So just for fun, if I decide to connect the colors to my base color here, of course now it's going to show white because it doesn't have the sphere, this preview sphere doesn't have any vertex colors. But if I apply this material to the objects, you'll be able to see it. I think it's compiling the shader. Here we go. Yeah. So you can see now all the vertex colors that I painted now are visible. I don't think people will be using it for coloring the meshes like this, but most of the time you will be using to do some special effects like blending between two textures or creating any special effects you want. The last example for vertex shader is offsetting vertices. And this is really cool because you can do a lot of cool effects with it. I think Martin showed us a very good example for animating tree leaves and whatnot. But you can like do other things also. Let me show this example here and how I'm going to show you how to use it actually. So here I have a teapot with the material. Let me grab the material for that teapot. I'll open it here. So what I did, I connected a vector to the word position offset. This is the port that allows you to control the offset of your vertices. So let me close this guy here and bring this to the side. Oops. Okay. It's hard to navigate with one screen. So if I change, like I have this object here, if I start adding some values here, let's say I want to have a vertex offset of 500 units or 500 centimeters on the x-axis, I just set this, compile the shader, and once it's compiled, you will notice now that the teapot is, boom, suddenly offset at 500 centimeters on the x-axis. This is boring, it's not really interesting, but what we can do is more interesting stuff. So I have already some simple logic here. I can explain to you later. Just let me show you what this does. I'll connect it to this guy over here. Compile the shader. So it's back. So now this vertex shader, what it does, it allows me to move the teapot as I want, but once I move it direct to the ground, it will squash it. So the animation or the deformation that you are seeing here is completely processed on the vertex shader. I don't need to do any additional setup. I don't need to do like morphs or skeletal animation or skinning or anything. It's all happening in this vertex shader. I have this logic here that controls this. It's very simple. I'm taking the position of the object, and I'm checking if it's below 0, do this. If it's above 0, keep it as it is, and outputting the result to my vertex offset. So you can do a lot of interesting things with it. And we saw already some practical example with the leaves animation. There is other also very common examples, like you can use it for cloth deformation if it's not really complex. We can use it also for water displacement if you have an ocean or something and we want to do the deformation for it. And of course, the foliage wind animation. So think about it as a procedural way for deforming your meshes without having to do any extra setup in advance. It's really cool. So a question, why we animate this way? Why we just not go through the classical approaches and do skinning or do morphs and whatnot? The basic answer is, of course, scalability. With this approach, we can animate a high number of vertices with a very low performance cost compared to other approaches. Plus, of course, the workflow, sometimes it might not be scalable to do like animation setup for certain cases. So if we imagine a forest that has millions of vertices or millions of leaves and we need to animate all of those, it will be a little bit tedious. And of course, it will be too much costly to do it with the classical approaches. Now, the drawback of animating with vertex shaders, of course, as also Martin touched on based on this is purely a visual effect. It doesn't update the scene state, so the CPU is not aware of what happens on the vertex shaders, because as we saw earlier when I showed you the threads between the CPU and the GPU, that at the point where the frame reached the CPU already started processing other frames. So there is no way to go back and update the CPU and update the scene state. So if we have physics, collisions, or any logic that depends on the mesh, it won't work. So it's very ideal for local deformation, I would say. It will be really useful. Now, in terms of performance, we need to keep in mind that, of course, the complex our logic, or the more complex our vertex shader, the more performance it will be costly. And of course, the more vertices we have in our mesh, the mesh we are deforming, it's going to be a little bit slower, but still it's going to be scalable. That's okay. So one common trick that we can do is we can disable complex vertex shader effects on a distant geometry. Because actually, at one point, people won't be noticing this, like the local animation or local deformation at a certain distance. Questions?
So the question I've got is in regards to the vertex shaders, and specifically, would it be possible to record the state of it not for the scene state, but basically, can you turn, let's say, your teapot into a melting teapot so that it treats itself like a particle system rather than a procedural animation?
Here's the thing, like you can do many things, of course. However, you need to keep in mind that there is a cost to this. Because if you remember, again, when I explained the hardware architecture and the transfer speed, if you want to bring back anything from the GPU back to the memory, it's going to be 100 times slower than what it used to be. So it has some cost on it, but of course, if you need to do something like this, and you have the access to the code, like you can do it.
Hi. So I'm assuming that the rendering thread first processes the shaders, the vertex shaders, and then draws it on screen to prevent any objects being occluded or being off screen and still being rendered?
So if I understand the question, you're asking if the GPU when it starts rendering the object, it doesn't occlude anything, or?
Yeah, so does it first process the vertex shader and then calculate occlusion?
No, that's a very good point. No, it calculates the occlusion, then calculate the vertex shader. And that's a very good point because you raised here. Because what happens if your object is decided to be not occluded, but you have a vertex shader that is pushing it outside your screen, it will still be processed. So you are wasting some vertex processing here. So yeah, that's a very good point you raised.
Okay, and then the second question I have is, how does it work if you use material instances to get that benefit of performance with the meshes being different?
Like if the meshes are different, like anyways it's going to be separate draw calls, like you can't really help it, right? But if you have the same mesh, and they have both the same material instance, they have to share exactly everything. If there is anything different in your material instances, if the mesh is different, it's going to be anyways a new draw call. So you can't really control if you have different properties.
When importing a model, an animated model from Max or Maya into Unreal, it's either done with a skeletal mesh, right? Is there a way that it can be, you can export animated vertices
Exporting animated vertices from Maya, you mean?
Yeah, from Maya or Max to
Yeah,
to
of course.
Unreal.
Like you can, it's going to be exported as morphed objects. So you can export your your shape animation and import them into Unreal, or you can use Alembic also. So yeah, you can. Yeah.
Right.
Of course.
Hi, yeah, I'm wondering what happens in the process of vertex painting in Unreal. What happens if the model changes? Like say, you know, you've added extra edges. You decide to add extra edges to, you know, add more detail in the DCC app, and then you re-export it. Do the vertex, the painted colors, do they match up still, or?
Yeah, I think, I'm not quite sure because I didn't test this, but I think you will lose your vertex painting. So if you re-import your mesh and you have different topology, it won't be able to preserve your vertex painting, so you will lose them.
I have two questions. First one is, let's say we have one teapot, we have an instance of a teapot, and the instance is deformed the way we've seen earlier. Are we gonna have two draw calls?
Yes, because here's the why you're going to have two draw calls. The first object is going to have a different material because it's not deformed, right? And
Yeah,
the
I'm
other
talking about the deformations that we're gonna have solely during render, not previously.
Oh, let's take another example. If you let's say a tree, okay, and you have multiple trees and they all use the same shader, even if the shader has deformation, it's going to be all one draw call if they are instanced.
Okay, that was question number one, and the other question is related to the previous question. We can get a cache, point cache out of Maya, for instance.
Yeah, of course.
Can we apply it directly on a graphic card as a deformation?
I'm not sure how the Alembic pipeline works in Unreal, but I'm quite sure you can import like point cache or vertex cache from Maya or any other software and play them back in Unreal. By default, I think those will be evaluated on the CPU, not even on the GPU. If you want to do that.
That was my question. Can we go straight to GPU? Can we propagate that?
Yeah, I think it's very possible, but you need to develop your own shader that does this.
Okay, good to know. Thank you.
You're welcome.
Hi, this also has to do with the question about altering the model. So you can't like vertex paint and then like bake that out into a map that would be in like UV space or something. So as long as your UV tiles didn't change.
Like you were asking if you can paint vertex painting in
yeah, and then like colors? If you up-resed your model or something, but it still had the same UVs.
Yeah, you can do this. Like it's not available natively in the editor. I think you need to create your own blueprint that bakes vertex colors to a texture map or something. It's doable. Yes, you don't need to do any extra like code in C++ or anything. You can do everything inside the editor itself. But we don't have now like a tool that with one click, yeah, is going to bake your vertex color to a texture so you can use them. Yeah.
So I mean, this is actually quite relevant to something I want to do as well. Something like a wet map.
Mm-hmm.
Would that be something you want to do with a vertex shader, or would that be like basically I don't know, objects colliding on a floor and it basically leaves a wet map behind?
I think for wet map you need more details because I'm trying to imagine if you have a low-res mesh and you depend on vertex shader to calculate your map, you might not have enough resolution to capture the details if you have a small object or something like this. So probably you will need to rely more on a pixel shader to do this, more than a vertex shader.
Any other questions? Okay.
Cool. Okay, so we're done now with the geometry processing. We can move now to rasterizing and G-buffers. So draw calls are done, like vertices are done. the GPU now is ready to render some pixels. And the way it does it, basically it takes the triangles that are already projected, because we saw earlier how the vertex shader projects our position, our vertices from the local space to the screen space, and basically start calculating the colors for each pixel that belongs to this triangle. So if you see here on this magnified pixel grid, we have a blue triangle, and the rasterization for this triangle gives us those orange pixels. Now, the thing that need to know, it happens draw call by draw call, again, to be more efficient. Then it goes triangle by the same order it is submitted to the GPU. And similar to the vertices, for pixels, we have pixel shaders that is responsible for calculating the final pixel color. And its input generally are interpolated vertex data, texture samplers, and other things. One thing to keep in mind when rasterizing is when we have dense meshes, especially if we are rendering them at a far distance, what we might end with is we have processing a lot of vertices just to render a few pixels. And here what we have is basically a waste of vertex processing. So if we have, let's say, a 100,000 triangle object that is like very, very far like from the camera, and is going to be few pixels big on the screen, we are paying the price for vertex processing 1,000 triangles just to render a few pixels on the screen. So we need to keep this in mind. There is also another thing to consider when we talk about pixel processing is overshading. And this is due to a hardware design. Usually GPUs doesn't process pixel by pixel. What it does, it processes quads of 2 pixels by 2 pixels. So again, if we have a very tiny triangle or very thin triangle, we might end processing 4 pixels just to shade only 1 or 2 pixels out of those quads. To visualize this, we can take also this graph here. I have a grid. The gray grid is basically our pixels, and we have the orange grid on top, which is the pixel quads that the GPU can process. So if we have a tiny triangle like this one, ideally we would like to rasterize it by only having 3 pixels. So we just need to process those 3 pixels to output the final color. However, in reality, this is not what happens on the GPU. The GPU needs to process 12 pixels just to render us only those 3 pixels at the end. So here we see like our first waste of pixel processing for small triangles like this one. Now to make it even worse, let's add another triangle beside it. So what happens is we need to shade those 2 pixels, but again the GPU, no, I'm going to process those 8 pixels. So we are wasting now more than that before, because we are processing the 8 pixels twice just to render those 2 triangles, which is quite a waste. To visualize this in the editor, we have a special mode called quad overdraw. I think that's an old term. That's why it was a little bit confusing with the overdraw problem. But it's recently referred as overshading. And here, let me show you that in the editor on that level. So if you switch to that mode, we can see anything that is dark blue, that means those pixels are processed only 1 time. If we see, like we move on to the green one, that means it's those pixels are processed 3 or 4 times, because either we have very tiny triangles, like in this case. You see here, like those spheres, they have a lot of triangles. And when I get close to them, they are getting bigger, so that they are processed less times. But when I get far of them, they get more green, and obviously will be at one point even, sorry, oops. Yeah, so we are almost now having solid green. That means all those pixels are processed 4 times because we have very tiny triangles on those areas. So to keep in mind, again, triangles are more expensive to render when they are dense, or when we are viewing them from a very far distance. So it's important to have LODs and culling, because otherwise we will be wasting a lot of vertex processing on this and those triangles. And same thing if we have, like this is more related to topology, trying to avoid very thin triangles that are rendered in an efficient way. And the last thing, of course, the complexity or the cost for overshading is directly related to how expensive is the pixel shader. So when we have an expensive pixel shader, those guys over here will be really expensive because we are repeating the expensive pixel shader 4 times at least to render with those few pixels. Talking about thin triangles and bad topology, this is a very common example that can cause a lot of overshading because you see here all the triangles of the cylinder are all merged in this one point, and it's already now we are going to have a black spot because we have a lot of intersections. But if we want to visualize this in the editor and see how the overshading works with it, you see that clearly how the pixels, let me switch to wireframe. Like the pixels here in the middle are all green, even from a close distance, because we have this thin triangles happening all the place. Oops, sorry, wrong mode. Yep. Still wrong one. Yep. Made it this time. So yeah, you see the green spot in the middle where the triangles are merged. Same thing, let's look at this example here. This is a very thin object, like with triangles that are spanning and long, very long. So ideally, we need to have something like kind of uniform. It's okay to be some like non-uniform quads, that's fine. But you need to always be careful about the density and the topology. Okay, so we're done with rasterizing our triangles or our meshes to pixels. So what we end with is, in case of deferred shading, we will end with G buffers or multiple passes. And in the case of forward shading, we will probably end with one pass, which has the final shaded and everything. So we will continue talking about deferred shading because that's, again, the default rendering mode in Unreal 4. So what happens for each frame is the engine renders multiple passes or multiple G buffers, and each one of those G buffers encodes special data that can be used later for lighting and shading. And we refer to them as G buffers. In the editor, let me go back here. We can visualize all the G buffers that the engine generates from this menu. So here, if we go to buffer visualization, we can see a full list of all the G buffers that are generated by the editor. So we have, for example, the base color, which has only the materials and the texture colors without any shading, without any extra information. We have some material properties like roughness, for example, and so on and so forth. There is this option here which can show you an overview of all the buffers. So let me expand things here. So you see, like on the top right, we have the normal buffer, we have subsurface. In this case, we don't have any subsurface. So we have specular, base color, and so on and so forth. So this is the base color. This is the normal buffer also. It's very important for calculating the shading and lighting, as we will see later. And there is all those 3 different G buffers that are used for calculating the material properties like roughness, metallic, and specular. Also, Unreal gives you a very good thing, which is a custom buffer, a custom depth buffer that we can use it to output any extra information we want. Most of the times, I saw people using it to generate additional mask that can be used in chroma keying and whatnot. So it's useful, but it's not only created for this specific reason. You can use it for anything else if you want. Now, in terms of performance, we need to keep in mind because for each frame, we are generating multiple passes or multiple G buffers, and all those are stored in the memory, and they have bandwidth, so we need to keep in mind that there is some cost related to that on memory, and the cost is directly related to the resolution of our G buffer. So when we are rendering on a 4K resolution, our G buffers will be at least like 16 times maybe than when we are rendering on 1K or something like this. So we need to keep this in mind when we are using deferred shading. Questions about G buffers and rasterizing?
Could it be possible to see a quick demo of the chroma key?
Unfortunately, I don't think I have a scene available with me. Like, let me check my maps. No. But what I can do is, I think there is many, like even if it's listed in the documentation, if I'm not wrong. So there is a few examples already on the web about how to use the custom depth buffer and use it for chroma keying and other applications. Yeah.
Any other questions?
Okay.
Proceed.
So now we reached the step of lighting and shadows. Now I'm going to separate the lighting and shadows to two main approaches. Of course, this is the separation mainly for this masterclass, but it doesn't have any technical implications. So we're going to separate between lighting and shadow that is calculated in real time. So it allows for dynamic lights and dynamic objects to be considered. And we are going to have another type of lighting and shadow, which is very specific to static or pre-calculating lighting and shadows. So we will start by covering the first one, which is dynamic lighting and shadows. And it's important to keep in mind that the approach that is covered here is very specific to deferred shading, because as I mentioned, forward shader, when it generates the final pass, it already done all the lighting and everything. So this is mainly specific to deferred shading. So the way lighting is calculated in deferred shading is basically based on the pixel shaders completely. It represents dynamic lights, for example, point lights, as simple primitives. In case of point lights, they are represented as spheres. In case of spotlights, they are represented as cones, something like this. So those primitives acted as masks, and any pixel within that mask is going to receive the pixel shader for calculating the lighting. So if we want to visualize, this is something what we can see theoretically. Again, this is not in reality, how a mask for a point light with its radius is going to look. And then this mask is going to be used to determine exactly which pixel from our scene going to be receiving the pixel shader for calculating the lighting. So for this point light, we can see all the blue pixels are going to be affected by that point light, depending, again, based on its radius. Now, if we have another point light, it's the same thing. We're going to generate a mask, and we need to identify which are the pixels that are going to receive the pixel shader. So here, for those pixels that are in light blue, that means those will be calculated by the pixel shader twice, once for the first light and another time for the second light. And of course, now the pixel shader need to consider all the lighting properties, like the light color, the fall-off, intensity, anything. This is going to be directly considered in the pixel shader. It's not going to be represented in any buffer, but I'm just have this image to visualize it, but it's not going to be like that. Now, the next thing, of course, we need to use the depth buffer that we already calculated early before to know which pixel is going to be within the range of the point light. So we use that. We have the final pixel that are affected by the point lights. And then we use the normal buffer to shade the final pixel. So depending on the normal direction and the point position, we can calculate, okay, this pixel will be shaded more than this pixel will be a little bit darker, and so on and so forth. So at this point, we have the basic lighting shading. Now we need to go on and figure out the shadows. For the shadows, the most common technique in real time for calculating shadows is referred as shadow maps. And the concept behind shadow maps is basically checking for each pixel if it's visible to a given light or no. And in order to do this, we need to render a depth pass, but now instead of having it from the camera point of view, we need to render it from the light point of view. Using this depth pass, we can now tell if this pixel from my scene is visible from that light or no. Once we have this information, we will have something like this, where we have a mask of, okay, those pixels are going to be in shadows because they are not visible to that light, and those pixels will be visible, so we have them masked like this. And then we combine the results with the shaded results. Once we have reached this point, we just take those two calculations, those two new buffers, and composite them on the other buffers that we have to get almost the final results. We are still not ready to finalize it, but we are very close now. So what's the main advantages and disadvantages of having dynamic lights and shadows? The first thing, or the first fact about it is, as we saw, it uses the G buffers. So we already have this information, so it's easy to add lights and remove lights without any lot of overhead. And because it's all dynamic and it's calculated in runtime, lights can be changed, we can move them, we can change the color, we can do whatever we want, and all the lighting will be updated properly. And third thing is, we don't need any special preparation for the objects. Like what we have in the editor, it will be lit and shadowed perfectly without any extra attention. However, the main disadvantage with this, because it's dynamic, shadows is a little bit expensive, even with deferred shading, because if we remember, if I go back to this slide here, we need to generate a depth pass from the light point of view. And in able to do this, we need to go back and go through the rendering process again from the beginning. So we need to go and process the vertices, we need to project them, we need to calculate many things. So all the optimization and the process we gone through for rendering the main passes, we need to go and do it for this one. So you need to think about it as if we are almost rendering the scene twice just to calculate the shadows. So shadows is expensive relatively. Now in terms of quality, because shadows are expensive, we always try to compensate that by lowering their quality a little bit. So we have like smaller buffers, or we try to do other tricks or approximations to make them more efficient. And for the dynamic lights, because again, as we mentioned very early in the masterclass, we can't afford doing ray tracing. So effects like radiosity or global illumination or any of those ray trace expensive effects, they won't be calculated. Same thing also, like we used to have in V-Ray or Arnold soft shadows and area lights and all those kind of nice quality shadows. It's very expensive to do them in real time with dynamic shadows. It's possible, of course, I'm not saying it's impossible, but there is high cost for doing this. So most of the times, dynamic shadows often look like very sharp if we have high resolution shadow maps, or like blocky. Okay, so some of the important points to keep in mind for the performance. Small dynamic lights is relatively cheap and deferred renderer. However, once we start having larger lights or bigger radius of those lights, it's going to be more expensive. Sorry. The radius is going to affect how many pixels from our final buffer is going to be processed by the pixel shader. So it's always important to try to have as small radius as we can for the point lights or any type of lights, of course, and try to avoid having a lot of overlapping between those lights. Let me show you a simple example here with this screenshot. So here I have two dynamic lights. They are point lights. You see, like, they look almost identical. However, if I showed you the radius for both, they are totally different. The one on the left has much bigger radius than the one on the right, so the one on the left, obviously, it's much more expensive to calculate. However, if you look at the result, they are almost the same. What I did only to have this smaller radius is I just tweaked the intensity, the fall-off, and a few other parameters to keep the same results, because I need to have some good quality and I want to have control on how things are lit. But at the same time, I can still make them efficient by controlling those things. For shadows, the easiest thing, of course, to help the performance is turn off shadows for lights that are not really needed. And also we need to keep in mind, because as we explained earlier, shadow maps go through the rendering pipeline almost one more time. So it's really affected by the triangle count. if our scene is really heavy in triangles, the shadow maps calculation will be also heavy, not only the main rendering. So one trick we can do for optimizing or helping the shadow performance is to try to toggle them off at a certain distance when they are not really contributing to the final frame. Okay, questions?
I actually have two questions. The first one, are there plans for Unreal to release a linear light?
Linear light?
Yeah.
Like you mean linear area lights or some?
Yeah, exactly.
Neon?
I mean, no, like light that is casted parallelly, or not in a
directional light. You mean?
No, not directional light. No, I mean, let's say
area lights. Okay. So yeah, of course, if that's what I'm going to cover in the next lighting option, which is static lighting. With static lighting, you can have more complex lighting shape like linear lights or any shape you want. So if you want to have something
because a strategy to do that, the only way to do that is to tick the thing that says use emissive to light static objects, in which you can create any shape of light you want. I was wondering if you can do that without having to have the object be static. You know what I mean?
Yeah, it's going to be again a type of area lights. So you have a mesh that you want to use it to light your scene or something like this, if I understand well the question. So yeah, you can do this. Like the default point light and spotlights have some parameters. Let me show you actually that in the editor. You might know those already, but just in case, let me see if I have a point light. Yes, we have one here. So you have, for each light, you have a parameter called source radius and I think source length. And with those parameters, you can control the shape, not exactly the way you have the flexibility when you have an irregular mesh, but it can give you very decent representation if you want to generate some area light, nice area light with soft shadows. But unfortunately, if you want to have like any mesh that you want to use or a specific shape of light, you need to use a mesh, and as you mentioned, like you toggle it, use an emissive, and go through the same process.
Hello?
Yeah, hello.
So imagine I have a character, and let's say he's flying through the sky. If I wanted to have light and volumetric light and dynamic lighting emitting from his eyes, can that be done with the same dynamic light, or would that be a separate process?
So here's your question has actually 2 points, which is really interesting. For volumetric light, there is many ways to approximate them in a cheap way. So you don't need really to use actual or real light components to have this volumetric effects going from the eyes. You can do it with some meshes that looks like a cone or something and apply some shaders to give you some interesting results, like to make it feel like a volumetric light. That's what? It's going to be cheaper on the memory and on the GPU also. Like this approximation is really common in the gaming world, and it's really easy to achieve, and it's cheap to render. There is also more expensive ways to do it. So you can use the light component, and you can assign create some extra fancy light shaders for it. But yeah, that will be more expensive on the GPU when it's going to be rendered. You're welcome.
Question from online? The online question is, can you use a separate LOD or HLOD for shadowing, for shadow casting?
That's a very nice question. I hope we have this in editor, because it really helps the shadow calculations, the shadow maps calculations. Instead of going through the triangle, the heavy mesh triangles and processing it, we will be able to use the lower mesh to make it even faster. The only caveat with this approach, yeah, it's going to be much faster to create the shadow maps, but we will have some inaccuracy with the shadows. So you might have your mesh that looks has some details, and the shadow maps, because it's using a lower LOD, won't be following the exact details from the higher mesh. So it has some caveat, but it's very interesting, and yeah, I would like to have it in the editor, but not in this version, I think.
Other questions? Okay. Go ahead.
Okay. So now we are going to talk about the other approach for doing lighting and shadows, which is the static lighting and shadows. So why we need this other approach? Because obviously we saw dynamic lights and mainly shadows very expensive. So as we mentioned earlier, like it's very common that we try to offload or pre-calculate some of the expensive things in advance and only use it in real time, use the results of it in real time. So we refer to this in Unreal by static lights or static shadows. And usually this information is stored as a texture, which we refer to as light maps. So basically a light map is, again, is a texture that contains the lighting and shadow information baked to it. Usually objects that have light maps requires additional UV for mapping between the object and the texture. And the way the light map is used is basically multiplied by the color information we have from the texture and other things. In the editor, let me show you a simple scene that demonstrates light maps. So here you see I have, let me remove the grid, a very simple scene that it looks to be lit. It has some lighting, it has soft shadows, it has many details, but if I show you my outliner, I don't have anything. I only have one static mesh, and it looks like this lit. So this is one example where I pre-calculated my lighting, I pre-calculated the shadows, and assign them to this object, and here we have like the final results. So the way you, let me show you the texture of the shadow map. So this is this is the light maps that is generated for that object. So you can see how like this is where supposed the cube to be, and this is its shadows and other things. And this is actually mapped to, open the static mesh, to the UVs, to a special UV on that object. So if I switch to the UV channel 1, you see this is the UVs that is used to map the texture, the light mapped texture to the object. I have another UV for the basic things. So in case, let's say I want to add now a texture to this one, I can go back to my material, and as I mentioned, I can multiply a texture information with my light map and output the result to my shader. So now when I compile the shader and go back to my scene, you see now I have a texture with the lighting calculated. Now, what I showed you, this is basically the same thing that I explained in the editor. So for a large scene, what we have, like when we calculate the shadow maps, the light maps, we have something like this, and we take the base color again and multiply it to have these results. Now, doing this manually, the way I showed you, it's not really practical because for each object, you need to go manually bake the light maps and create the UVs, assign them, multiply them by the texture. So it's a little bit tedious process. And able to accelerate this, Unreal provides us with a special tool for doing all this task. It's called Lightmass. So basically what Lightmass is a standalone application that handles three main things. It handles light rendering, baking to light maps, and integrating the results into your materials. And the last point is super important because it hides a lot of the complexity into your materials. You don't need, when you create your materials, to do something like this, to take your light maps manually and multiply it and do all this kind of things. It's already handled for you. So you just plug your texture to the base color or to the proper port, and you will have all the lighting information integrated for you. So it's really useful. And Lightmass, because it's offline render, it supports ray tracing, so you can generate nice lighting scenarios like with GI, with area lights, with all those kind of things. And also it supports distributed rendering over a network. So if you have a render farm, you can accelerate the light map baking with this. And of course, the quality of the light maps is dependent on some settings that you have control in the editor. So if I switch back here, so under the build menu, we have a high-level quality settings for how good is the light maps calculation is. The cheapest one or the most fastest one is the preview. It's really, this mode is very good for iterating. If you are really still working with your lighting, you are changing a lot of things, so you probably need to stick with this one. And once you are almost decided with the final lighting setup, you probably would like to move on to something like high or production. So this is really cool because it's easy, like you only have 4 or 5 options. But most of the times, if you want to dig deeper and control the rendering settings of light mass, you can still do this. So if you go to the world settings, you have a special section which is called light mass. If you expand it, you have a lot of parameters where you can control in detail the calculation for the lighting and the shadows and everything. And even though if this is not enough, because like you want to go much deeper and like control something like other parameters, you can go to the INI files for light mass and have all the full parameters exposed for you. But most of the times in real production, you rarely need to go to the INI files. Most of the, like all the important parameters that you need to control and affect the quality are already exposed to you here. And to make light mass also calculations more efficient and to get better quality, it's important to use the light mass importance volume. Let me show, sorry, load the level again. So, why we need to use this importance volume is basically just to tell light mass to focus its effort or the calculations within that volume where we have our objects, instead of just leaving it to calculate certain areas of the world that we are not really interested in. So if I search, I think I already have one here. So you see I have a volume that I already added, and I put it only around the interested area for my project, which is this one here. I have other things like those mountains and the sky. I don't really care about having static lighting on those, so I don't want for light mass to spend any time or energy calculating those. Everything what I need is all in this area, so that's why I created this volume around this here. Now, the advantages of having static lighting is, of course, it's super fast to calculate in real time because we don't need to do anything. It's already pre-calculated for us. However, on the same time, it increases memory because we are going to generate more textures to store the lighting and shadows information. The other disadvantage also, it sometimes takes a long time to pre-calculate, especially if you have large scenes with many high-resolution light maps. So it might take, it's like basically like offline renderers, like V-Ray. So when you have large scenes, instead of having minutes to calculate, it might be hours or maybe more. So the other also issue with it, every time you change something, you need to recalculate the light maps again. So that's why it's very important when you are iterating on your lighting to use the preview mode, because that will save you a lot of time and will calculate a rough lighting and shadows in a very fast way. And the final point, which we already covered, is those objects that we want to have static lighting, we need to probably generate special UVs for them. Now, the good thing is that Unreal already offers you a feature to generate the UVs automatically for. So when you import an object, and the import options, you have a checkbox for generating UVs for light maps. Or if you have, let me grab a mesh. And search for light maps. Yeah, you can, like this, for example, this object doesn't have light map UVs, but if I tick this one here, enable it, and then apply, it's going to regenerate automatically light maps UVs. So this might save you some time if you don't want to do it manually in the DCC. Now, in terms of quality, of course, it has a very good advantage where it can handle now complex lighting scenarios like radiosity or global illumination. Same thing for shadows. We can now render area lights with soft shadows and everything. So It's really cool in terms of quality. Now, on the other side, it's very dependent on the resolution and the UV layout. So when we have a low resolution light maps for an object, obviously the lighting or the shadows won't be much detailed. Probably it will be blocky or blurry. So this is something that also to consider. And in certain cases, when we have bad UV layout, we might notice some seams or bleeding between the pixels. Now, in terms of performance, we already know by now that static lighting always render at the same speed because we are not calculating anything in runtime. All the calculations happens before. So if we have one light or we have 100 lights, it's going to be the same in runtime. And we already know that also the light map resolution is affected mainly, it only affects the memories and file size, not the frame rate. Now, if we are really concerned about the bake times, there is some of the factors that affect them. Light map resolution, the higher resolution, the slower the light map baking will be. The number of static lights, if we have many lights, obviously is going to be slower. The quality settings, this is also obvious. As I mentioned, when we need to iterate, it's important to be in preview or low settings because it's much faster than having the higher settings. And the last thing, which is really interesting, is the radius. So when we have lights with big radius, similar to how they are expensive in dynamic lighting, they are also expensive when we bake them. Okay, so one general guideline that can help having some good quality with static lighting is to make sure you have constant or uniform light map resolution. Because when you have like big differences between the resolution of light maps, like the viewer or the app or the experience will be very obvious where, for example, here in this case, we have the blue low-res light map, so like the textures or the shadows will be very blocky, while the ones here with the red will be super sharp, so it will be very obvious, like the difference between those. So it's always good to have some sort of uniform resolution across all your scene. So that's it with lighting and shadows. Again, the best strategy is to try to mix between both systems. And you can do this. Like you can have static lighting and dynamic lighting at the same time. So like very common case where you can use static lighting for weak or distance lighting or for indirect lighting because this is the only option to have indirect lighting in real time at the moment. And we can keep dynamic lighting as an interactive layer for object that moves or lights that change or moves during runtime. Okay, questions about lighting?
Sorry, me?
Is there any way to get access to the light-baked maps outside of Unreal?
There is a way to access them inside Unreal, actually. So let me show you that here. So if you go to the light map settings, and you expand this hidden thing, you can see, like I have for this scene, 118 light maps already generated, and I can click on any one of them and open them and see. So you can access or debug them, see how they look like, but I don't think you can save them. Yeah, but it's going to be saved again to the build data, which is like it's not going to be an individual texture that you can export outside Unreal.
Thank you.
You're welcome.
If I remember, in the Fortnite trailer was all dynamic lighting. So I would like to know, how do you fake indirect lighting with dynamic lights?
How you mix dynamic lighting and indirect?
How do you fake indirect lighting with dynamic lights?
It's not really faking. Like Unreal, the new versions of Unreal, it has a new system for generating dynamic lighting in real time. I think it's still experimental. It's called light propagation volume. It's basically a volume that is attached to your camera, and it calculates indirect lighting in real time. So you can enable that by switching an I value or something. But again, like you need to keep in mind that this is it has a lot of high cost on the GPU. And the other thing, you won't be able to get detailed shadows or indirect lighting from it, like what you do with light mass. It's going to be, I think, for now, the voxel is going to be 64 by 64. So it's not a lot of details that you can gain of it. It's still good if you want to have like ambient indirect lighting, like something that give you some like bounce colors or something like this. It's cool, but you won't be seeing like soft shadows coming from area lights or something like this. It won't be. It's not enough. It doesn't have enough details to do it. Yeah.
Question from online?
Yep.
Can you import a IES file from like a photometric web or some within a light fixture?
Yeah, I think IES files are supported in Unreal. So if you pick any light and let me see. Oh, it's already here. So if you go, there is the light function. No, yeah, that one, sorry. IES texture. So you can specify an IES texture here. In my case, I don't have any available. I didn't import anything. But yeah, of course, if you import an IES texture, you can use it for your light, and it will work perfectly. And it will work also dynamically, so you don't need to bake. So this is real time.
Yeah, the online question is, does the light mass importance volume ignore the light mass calculation for the geometry outside of it?
That's a good question. I'm not sure if it completely ignores it or it's just give it a lower priority in terms of rays, because like what light mass does, it's like other ray tracers. It casts millions of rays everywhere. So instead of having those rays spread across all your level, the importance volume will try to keep them inside this area to get better results in a faster time. So if we have objects outside this volume, probably they will still get some rays, but it won't be as detailed as the objects inside it.
Is there any plans to support dynamic light mass baking in real time?
I think, again, it's the same feature that I just mentioned. It's light propagation volume. It's kind of, you can think of it as a replacement, a dynamic replacement for light mass. But again, for now, it's a little bit expensive to evaluate if you are targeting a high frame rate. And at the same time, as I just mentioned, it doesn't give you a very detailed quality because the resolution for the volume is not so high. So if you are okay with having low resolution or just general indirect lighting, yeah, it's perfect. You can enable it and use it.
So I was thinking more kind of like a real time on a separate thread, and as it goes along, you can bake the light maps on the geometry that you're seeing. So you get the quality as the game goes on, for example.
So like using the dynamic solution to bake on the fly, you mean?
Correct.
That's interesting concept. Yeah, I don't know if. But at the moment, no, I don't think there is any plans. Like what we have now, it's this feature that runs in real time. It's still experimental, so I think the near future plan is to stabilize it, to make it more performance, so it's more usable in practical cases. And at one point, maybe we can allow to change the resolution so you can have better results.
I have another question from online. Can you intercept or modify the light maps effects in a shader? In other words, darken them in real time?
No, the light maps that are generated by light mass, they are handled at a low level step, so you don't have direct access to it in your shader. The only way if you want to control your light maps in the shader is to do them manually, the way I showed them in the previous example.
Stupid question. So the light mass will overwrite the light maps that you might already have on the objects. The light mass volume will overwrite the light maps that you already have on the objects.
No, actually, what the light mass volume is basically, it's a way to optimize the calculation time and the quality for generating the light maps.
So it will use those light maps that you
Yeah, it will help to generate those light maps in a faster way, and it's going to be it has more quality. Yeah.
Anybody else? One more. Pardon me.
Once you've done your light map calculation, can you disable specific objects and have them not be recalculated when you do another calculation?
Yeah, that's a feature I would like to see a long time ago, but unfortunately at the moment, no, it's not possible. If you want to update a certain object, you need to recalculate the whole scene.
Okay, proceed.
Okay, cool. So then the last step in the rendering pipeline is post-processing. I think this is a step that most of you are familiar with because it's almost the same in the VFX. So basically what are those post-processes are visual, like full screen visual effects that are applied at the end of the rendering process. And because we already have a lot of those interesting information in those G buffers, so they can be used to calculate some of those post-processes. And the whole thing is basically done using a pixel shader. Here are some examples for some of the common post-process that Unreal supports. Actually, let me show you them in here in the editor. So if we go to this menu here, we can see a list of post-processes that are enabled. So we have bloom, we have color grading, depth of field, eye adaptation, and so on and so forth. And we can easily visualize the result of each post-process by just enabling and disabling those. So if, for example, I want to disable a bloom, you can see now how the scene looks like without my bloom. I enable it again, disable. Same thing for other type of post-processing. Now, in Unreal, in order to control those post-process, usually what we do is we create a post-process volume. I think I already have one here. Yeah, I have actually a few. So for each one of those volumes, you have a lot of control and exactly how you want your post-process. So you have a lot of detail control on the color grading, for everything, like for shadows, for like white balance, like it's really, really detailed. Same thing for lens effects. So we have chromatic, vignette, like grain. Of course, bloom, we have like different methods of bloom, one which is the standard one we see here, and we have a more realistic one, which is based on FFT. Auto exposure, like many things. I think if we want to go and explain all of those, we'll need a separate masterclass by itself. And on top of each this, if those are not enough for some reason and you want to have a specific post-process, you can still do this. So you can create a material. Let me go back here. And in that material, you just need to switch from default surface that is used usually on objects to a post-process. So once you did this, you can use this material in the post-process chain, and you can have any effect you want. Like, let's say you want to do some special effect that's not available here in the default ones. Even those are really versatile, but you can create a custom one and assign it to the post-process volume. I think it's under features. Let's try search. Yeah, post-process materials. So if you expand here, you can assign as many post-process materials you want. So I can say asset reference, and I can pick my material from here, my post-process material. And this material will be applied on top of the post-process chain. So this is really flexible. You can do any kind of effects you want with this. So in the next few slides, I'll just give you a very fast highlight on how some of the post-processes are calculated. We will start with the bloom. So the first step is basically extracting the highlight pixels from the color buffer, and then blur it. The way we blur the buffers is by downscaling them and then upscaling them with filtering. So we got something like this. And sometimes we like to add some dirt texture to the bloom, so we multiplied and we got this result, which will be ready to be composited with the final buffer we already have. Another also filter, which is depth of field, so we blur the frame, same thing we did before, by downscaling and upscaling. we use this time the depth buffer, and this is one of the examples where we are starting using some of the existing G-buffers to calculate post-process. So we use the depth buffer to specify which pixel we need to blur depending on the depth, and then we have all the results, all the calculated post-processes applied on each other. So we can see the bloom here from the windows affecting, like bleeding outside it. We can see this wall blurred, and so on and so forth. Of course, the way the explanation is oversimplified. Like in reality, the calculations is much more complex than this, and it's more accurate than the way I explained it. But just to give you a rough idea on how it works. Okay, so a few performance implications about post-process. First thing, because it happens on the final buffer, so it's heavily dependent on the resolution. The more resolution we have, the heavier the post-process will be. And the other thing, of course, which is obvious, it's also the cost of the post-process is going to be dependent on the shader complexity. So if we created a very complex post-process shader and assign it, that might affect our performance on the GPU. And for some post-process parameters also, they might make a difference in the performance. So if we have like a very huge radius for the depth of field, that will be also a little bit more expensive. Okay, so I think we can have some questions.
I had a question about the screen space reflections and just, we spoke a little bit before about the benefits of that, something being off camera, not being reflected in the edges potentially. But then there was a couple other methods of actually getting reflections in the engine.
Yep.
Are those considered just superior but more costly, or are screen space perhaps a preferred way to go?
It's not really superior. It's more about trying to have multiple solutions, blend between multiple approaches to have the best results with the best performance. So the problem with other approaches, it's not a problem, it's basically just the way it works. They're expensive to generate. So if you think about cube maps or like this cube map reflections, when we need to generate them, we usually need to render the scene again, probably multiple times in order to generate the cube map. So this is a very expensive process, as you expect. So in order to make it a little bit cheaper, what we do is we have a very low resolution render for it. So most of the times, if you see the default resolution for the cube maps, I think it's 128 or even less than this. Let me see, just double check that. Capture offset, no. Yeah, but anyways, like usually it's very low, project settings maybe, yeah. It's very low res render targets. So we do this again to help to compensate the performance impact that we get when we generate those cube maps. So you don't have a lot of detailed reflections out of cube maps most of the time. So in order to have better details, we add on top of it screen space reflections to get this extra layer of details. Yeah, so you can use both without any problem. So the screen space reflection will add some details when you are near the object, so you can see more details. Also, it has some quality issues sometimes, but it gives you more details. And you can keep the sphere reflections at lower resolution just for the bigger things. Of course, like if you can afford high resolution in the cube maps, you might not need the screen space reflections. You just crank the resolution on those. But it's up like how you want to, like what's the target frame rate, what's the budget for your scene. Yeah.
Is there a performance difference between using a post-process material and a post-process volume for a color effect?
Post-process volume for, sorry, what?
Applying a post-process material, which you showed, applying it to a particular view versus using a post-process volume.
Oh, so the post-process volume is basically, it's a way to specify the area where the post-process effect will be applied to. It's not going to have any like special thing. So here, what in my scene, let me show you again, post-process. So I have few volumes over here. So basically, it's very similar to how light mass, importance volume, or other volumes works. They just, those actors are basically a way to identify the area where you want your post-process to be, to get calculated. So it's not going to have any performance impact. Basically, all the performance is directly related to the material or the options you enable in your volumes. So if I go inside here, like the post-process volume, inside this post-process volume, like the settings, all the post-process settings are going to be applied here. If I moved on to the other volume, and I have different settings, I'm going to see a shift between post-process settings to another settings.
Hello, I had a question about the scene depth. I use the scene depth pass to isolate things in a compositing program, and I often get a whole bunch of those repeating rings after I guess the depth volume is recalculated at a certain point. Is there any way that we can change that parameter so that I don't get a whole bunch of rings in my depth pass output?
So let me show the depth pass. So I think you mean those things over, yeah. So basically, what's happened here, like usually the depth pass is encoded into a 16-bit buffer. So in order to capture all the depth details. So when we try to visualize this depth buffer on a 8-bit buffer that we have in the screen, we will see those effects. However, if you open this in render doc or you see the raw depth, you won't be seeing any of those artifacts. Like it will be smooth gradual between all the depth values. Yep.
I'm interested in statistics that Unreal provides about shader complexity. I think if in the shader graph, it does give you some information about how many operations the shader would require. Can you talk about what types of things drive up shader complexity and how to look at that?
Yeah, sure. That's a very good question, actually. So let me open a shader so we can look at it. Those are instances. I think this is a shader. Cool. Yeah, so here when I enable the stats, you can see some numbers. So for example, for this shader, even it looks a little bit complex, but still it's not that bad. It says here you have 132 instructions. So basically what the engine does is allows us as an artist or as a technical artist to use this graphical UI to create our shaders. However, at the end, it translates everything to a GPU language, which is basically HLSL, and ultimately is going to be an assembly for the GPU. And here in the instruction, what you see is the final translated code that based on this graph. It's not really, it's give you a very good indication. So the more instruction obviously is going, like your shader is going to be more expensive. But that doesn't really mean that this shader is going to be more expensive. Now let me explain what that means. You might have two shaders, one with 100 instructions and another shader with maybe 50 instructions. However, and the 50 instruction is going to be more expensive than the 100. And the reason behind this, because the one with the 50 instruction is using expensive math calculations. So usually, like if we're creating our shaders and we are doing multiplication or we are using addition, like those simple things are usually very, very cheap. So when we have like 100 instruction of multiplication and add, that's fine. But once we have something like sine or cosine, or like those, or for example arc sine, those are becoming more expensive. Or maybe if we have power, that's going to be expensive. So if we have 100 instruction of add versus another shader with 50 instruction that has mainly sines and cosines, that one will be more expensive. So that's why I mentioned this number is, yeah, it's a good guideline, but it's not accurate. In order to get the real accurate performance, you need to go and check that with the profiling, GPU profiling tool like this one. There is also other tools like would allow you to see the actual pixel shader, how it's translated to the GPU. So if I click here on the pixel shader in this pipeline, I can see for that object, which is, I think it's, yeah, this status here. Oops. Yeah, so for that guy, the shader that is, or the pixel shader that is applied to it, it uses all those textures. So I'm using like 8 texture samples. And of course, I can visualize each one of those. And I can also, this is the pixel shader, click on view, and see the actual shader that is translated to the GPU. So this is now, it's not even HLSL, this is more like assembly. This is the final code that the GPU used to calculate the pixel colors. So you see some of the calculations, like this is like for multiply, or probably for exponent, and so on and so forth. So this shader, it has 169 instructions. But again, this number is not the only factor that affects how expensive is your shader. Like, what are those actual functions are doing are more important. So for example, here you see I have a branching, which is really expensive. That's something that you need to avoid doing on in your shader if possible. That's why we have in Unreal something called static switch, which allow Unreal to optimize and knows in advance, okay, this static switch is going to be always true, so I'm going to remove the condition and bake it when it's true, and create another variation when it's false and bake it.
I have a couple questions online.
Mm-hmm.
One question was, can you access the downsampled post-process in the G buffer and use it to generate your own effects?
In the editor, I'm not sure, probably. But yeah, I know you definitely can access the G buffers in your shader. So you can, like, if you are doing a special effects like or a post-processed material, yeah, you can access them and do something. But I'm not sure if you can access a certain downsample of it. I need to investigate that.
Another question was just about examples of specific filter types like holographic effects and stencil effects, and examples that Epic might provide for those.
Yeah, of course, we can provide examples. I think in the documentation, we have a few interesting examples on how to create some post-processed materials. Let me see if we have internet. I can probably pull very fast. An example. Yeah. Yeah, like there is many examples on post-processed materials. So this one, I think we'll have some. So yeah, here you see like we have a scene that is rendered with default shaders and then apply some post-process to have like some toon shading or some outlines with. So it's very flexible, and like the way you add them, you create them with this nice UI using the graph, and then assign them to your post-processed material. Here is another example where you can do some video corruption or something like this. So yeah, there is many examples on how to do post-processed materials.
Question here. I've had an issue sometimes using planar reflections where it'll look great in the viewport, like if on a glossy floor, and it'll render out of the matinee really well as an animation. But if I'm looking through a matinee camera and I try and take a high-res screenshot, it just kind of doesn't work at all, and the floor looks matte.
I'm not sure if I can really repro this scenario because I didn't notice this before, but I think the best, in order to help you the best way, like just forward me the sample where you have the problem with matinee and reflections, and yeah, definitely we can look at it and see what's wrong with it, for sure.
Other questions?
What was the other one? I think I can get the faster.
It's a race.
So I have a question about these shader instructions. So what does the shader complexity visualization in the editor actually show? Does it only show the number of instructions, or does it also account for the type of operations?
That's a good question. To be honest, I'm not quite sure, but I expect it's only going to show you the number of instruction. It doesn't really consider the cost of each instruction.
Okay, so how would a user debug which shaders are most heavy in the scene?
So again, like with the shader complexity and the number of instruction you have in the material, it's a good indication. Like it's give you like generally the more instruction you have, the more expensive your shader. So that's a very good starting point to optimize your shaders. However, if you still find like certain shader, it doesn't really make any sense. Like you have a very low number of instruction, but it's still like costing you a lot on the GPU. In that case, the only thing you need to go back and use a tool like RenderDoc or other tools for GPU profiling. That will be a little bit more detailed or technical.
Other questions? Okay, proceed.
I think we are almost done because post-process was the last section of our rendering pipeline. So that's it for today, and yeah, thank you, everyone.
All right, let's see here. We plan to be sending out a questionnaire in which I'm sure some of you are probably interested in this material. Am I right? Would you like to obtain copies to this material? Then you need to sign up for online, and I believe Louis and Claudette will be able to assist you with that matter if you haven't already done that yet. So if we get your information, we'll be able to send you a link as to where to download all of this information and so forth, and hopefully you'll be nice and fill out the survey that we provide. Any last-minute questions on anything? Yes?
So this is more, hopefully, maybe a request or something for your future sessions that you're mentioning, but I would be extremely interested if you could do a session on blueprints.
Yeah.
That's a common question. That'd be a good one to include. Yes, over here.
Interested in getting multipass renders out of the engine in an image sequence.
Yeah, actually, you can do this. So if you are using a scene capture 2D, there is a special actor here, which is scene capture 2D when you add it to your scene. And here, yeah, you specify what you want to output. So in my case, I'm outputting the scene color in HDR, but you can specify, okay, I want to output the depth, or I want to output the LDR, or the normal buffer, or the base color. So you have some flexibility in outputting or writing some of the buffers you're already generating to textures, and then you can export them outside the editor and do something else with them.
Oh, sequencer can do that as well if you're trying to build like linear content. So.
Any other questions? Last minute? Yep, over here, Pascal.
Yeah, I've seen very interesting demos about V-Ray and Octane being integrated into Unreal. Can you tell us when we'll see that coming soon?
So,
hi, I'm Chris. I think V-Ray has announced their date. I can't speak for them specifically, but I recall reading very recently in, I think, CG Channel that they had announced, I think, Q3 of this year for integration into Unreal Engine. Of course, they showed it at SIGGRAPH this past year. They showed the preview of that with some of the Harley-Davidson content. So I know that's coming, and 2018 will definitely have their integration according to what I read. I don't work for them, so.
All the way in the back, Lynette.
Okay. Can I have this one?
Hi. I've heard that Unreal might support render targets. Is that true?
Render targets, like if you mean render targets by like the G buffers, but you want to output them, yes, of course. Like deferred shading is all based on having multiple G buffers or render targets that you can use them either inside your materials or like store them as external textures and export them.
Okay, cool, thanks.
Any last questions? Okay, we've got one more.
A light field renderer in Unreal from someone like, no?
I'm not quite sure about this feature.
Otoy or something like that going in?
Yeah, I'm not so familiar with it, but I don't, yeah. Sorry.
All right. I believe that will conclude for tonight's presentations. And we really appreciate for all of you who have attended. And we will have more information coming out soon about upcoming training events that will be being held. Some will be, again, in California and other parts of the United States and in Canada. So be on the lookout on our blog for that type of information. And we look forward to seeing you again at our next event. Thank you.